Like many of the speakers before me, I want to echo thanking the organizers for bringing us all together at this very, very unique location. And I also want to thank you for permitting me to present some of my work in front of so many friends and even more people that I've been admiring for many years from afar. So what I want to do is I want to talk about something that is maybe subverting expectations a little bit. We're in a session on the present and future perspectives of quantum sciences and technologies, and I want to advocate that in order to look into the future, we should look into the past. What I want to talk about is thermodynamics, and as many of you might know, next year, 2024, is actually the 200th anniversary of the invention of thermodynamics. Carnot published his first book in 1824. So I want to use a theory that is even 100 years older than quantum science and technology, which took its origins 100 years ago. Now, when I first was approached in July about what I might be presenting, I was maybe a little bit ambitious. I think it was Marlon who said that he had about an hour worth of lecture that he compressed into 20 minutes. And when I was thinking about what I could present here, I was more thinking about a 15-week course that I should give in maybe 20 minutes. And I'm not going to do that. So rather than giving you a very broad introduction, I'm going to focus on one and only one example of the type of problems that we're interested in and try to convince you that thermodynamic thinking and thermodynamic principles are interesting and important for the type of things we do. Now, before we actually get to quantum, let me make sure that we're all on the same page. And of course, you all know this. Thermodynamics is no theory, and you've all taken classes in thermodynamics. But when I say thermodynamics, what I really mean is a phenomenological theory that was developed to describe the average behavior of heat and work. Now, over the last couple of days, we've already seen that thermodynamics and thermodynamic principles can be applied across pretty much all length scales. I believe it was Martin who was talking about equations of states, and he was talking about nano clouds of fermions, and then at some point he dropped the phrase neutron stars. And here you already see the vast range of length scales where thermodynamic principles apply. However, and this is also something that is not often appreciated, is that if you say thermodynamics, you're actually lying. There is no true dynamics in thermodynamics. The only processes that are fully describable by means of conventional thermodynamics are quasi-static succession of equilibrium states. The only thing that you can say about real-life processes in thermodynamics is that you're dissipating something into the environment. And the purpose of thermodynamics is then to estimate how much we're dissipating into the environment, how much we're wasting, and to come up with optimal control schemes that allow us to minimize this dissipation. Now, when you hear the word thermodynamics, and we just saw a couple of turning wheels as a representation of engines, I think what you rather have in mind is something like this. So I was born and raised in Augsburg, so I really like this picture, because what you're looking at is the first operational prototype of the diesel engine, which you can find in the Industry Museum in Augsburg. Rudolf Diesel worked at the engineer school, and this is what he developed. Now, this is a picture that I took, I don't know, 25 years ago, and if you stand in front of this engine, it's almost as tall as this room, and I've never really counted, but it probably has something like a couple of thousand, maybe 5,000 moving parts. And in principle, of course, we know how to write down the Hamiltonian dynamics, the Hamiltonian equations of motion of all of these moving parts. But it's just too complicated. And thermodynamics in the beginning of the Industrial Revolution was developed to find universal control schemes, ways to minimize dissipation in these very complicated technologies without having to solve the microscopic dynamics. The reason why I'm saying this is because I believe we're very much in the same situation again. I think over the last couple of days, it has been called the second, third, and then eventually the fourth quantum revolution. So let me not say fifth quantum revolution, let me a little bit more prosaic and call it the rise of the quantum information age. This is just a random selection of pretty pictures that you can find on the web, and some of which we've already heard about over the last couple of days. But all of these new technologies are being invented that can do something useful. And of course, in principle, we can write down the microscopic equation of motions. The difference is now we have, I don't know, maybe thousands of coupled partial differential equations. And in principle, we know how to write down the Schrödinger equation for these, but we cannot solve them. That's the entire reason why we need quantum technology, because we cannot solve the quantum dynamics exactly. What I want to advocate is that thermodynamic principles and this very old, 200-year-old way of thinking about how to minimize dissipation still can be incredibly useful also in these contexts. Now, if you look at these devices, they don't look like engines. They're not even nano engines. They don't do anything useful in the sense that you can't stick them into your car and move forward. Rather, what they do is that they process information. Now, information is maybe something that you wouldn't necessarily relate to thermodynamics. However, this is not entirely correct, because also information has been recognized already 150 years ago, 50 years before the birth of quantum mechanics, as an important part of thermodynamics. And I'm not going to walk you through the details of Maxwell-Demon, you know this, but the essence is that taking measurements on the microscopic states of the constituents of a dynamical system, in this case gas particles, you can beat conventional statements of the second law in the sense that collecting information, the processing of information, can be used in order to do something useful, in order to do work. Surprisingly, it took a very long time, until about 10 years ago, when we finally formalized information as a thermodynamic resource and put into context that information should be treated by the same means, by the same mathematical formalism with which you treat heat and work. Now, thermodynamics of information has grown into a pretty big field, and there are many things out there. And as I promised, rather than talking about everything that I could possibly talk about, I'm going to hone in onto one specific example. And when thinking about the possible examples, I want to focus on computation. And when thinking about computation, an application of the framework of thermodynamics of information is typically called Landauer's principle. You walk into a department in computer engineering and computer science, if people know nothing about thermodynamics or physics, they do know Landauer's principle, which has been incredibly instrumental in the optimization of classical computing, of classical computers. Because what Landauer's principle does, it gives us a fundamental lower bound on the amount of energy that is required in order to process information. In particular, Landauer's principle states that in order to erase one bit of classical information, at least kBt log 2 of thermodynamic work are required. Now, if you look at Landauer's principle, then on the left-hand side, you have an average and you have work. And I could give an entire course on how to think about work for quantum systems, so I'm not going to do that here. But we will focus on some energy that is required in order to process information. On the right-hand side, you have kBt, and that arises from the fact that in classical information, what you assume is that the bit erasure works through coupling your logical degree of freedom to a thermal environment. Now, I think we all agree that coupling qubits or our quantum computers to thermal environments is not a good idea. Well, let's not do that. Let's not talk about temperature. So the one thing that I will talk about is this log 2, which is the amount of information that is being processed. One thing that I should say here, which will become important later on, is that you immediately see that what is considered computationally efficient or computationally reversible is not equivalent to thermodynamically reversible. The erasure of a bit is a logically irreversible process, a 2-to-1 map. However, the inequality becomes an equality for thermodynamically reversible process. And this is not it's just saying that what is thermodynamically efficient or what is thermodynamically ideal does not have to be computationally ideal. All right, so what do we have? We have a pretty old theory, a 200-year-old theory that included information 150 years ago, and we have at least 60 years of history and tradition of using thermodynamic principles processing of information. But most of this is really formulated for classical systems. What we want to do is we want to use similar techniques, a similar way of thinking to say something useful about quantum computing. And that means we need a new framework that is clean of thermal processes. It should be clean of classical arguments. It should be clean of a very classical phenomenology. What we want to do is we want to focus on what really matters in quantum systems. And again, letting me hone in on one particular example, I'm going to focus on unitary quantum operation. Now, we've seen much more sophisticated sketches of this in other talks, but what I do want to point out is that when we think about quantum computation, there is actually a multi-step process, and at every single step, there's an opportunity for a dissipation to arise. If you want to operate with quantum computers, you have to feed information into your quantum computer, you have to encode, then you have a black box. Here I have 3 qubits, but we've heard about systems of 50 qubits or 100 qubits or maybe 1,000 qubits that do something interesting and something useful. And I think it was Matthias who said that Well, it doesn't really help if the Hilbert space of the quantum computer is exponentially large if you can't extract the information in the end again. So in the very end, you have to decode. What this tells us is that if we want to think about thermodynamic principles and want to use this phenomenological framework, we do need to focus on the amount of information that is useful to us, to the amount of information that can be accessed by the decoder, which I called Bob here. So what do I mean by that? So a very simple example. So the simplest example that I could come up with that resembles somewhat bit erasure is a qubit reset. So assume that you have a quantum state that is prepared in an equal superposition of a logical 0 and a logical 1, up and down, and I apply a Hadamard. What you all know is that this Hadamard is nothing else but mapping the equal superposition of 0 on 1 onto 0. Now, these type of operations, these type of unitary operations are usually used as an excuse to claim that quantum computing is reversible and therefore things like Milano's principle shouldn't apply because the von Neumann entropy doesn't change. But the argument that I was trying to make on the previous slide is that the amount of information encoded in the quantum computer itself is maybe not the most useful quantity to look at. The von Neumann entropy, which quantifies the total amount of information encoded in the quantum computer, is not accessible to us. What is accessible to us is the information that is encoded in the logical states, what we're reading out. And if we focus on the Shannon information in the logical basis, which is given as in terms of the probability distribution over the logical basis, so we start with a 50-50 probability in 0 and 1 state, and we go to a probability distribution where we only have one state, then the change of the phenomenon, the Shannon information, von Neumann entropy in the logical basis, is log 2. Now, what we need to do is we need to quantify the energetic resources that are necessary in order to do this qubit reset. And all experimentalists in the room will certainly agree that there is an energetic price. If you want to control your qubits, you do have to shine a laser field, a magnetic field, or something onto your qubits. So it cannot be inherently for free. Now, in this framework, when talking about unitary gates, we often don't have a notion of energy. But as I was saying, experimentally, there's a clear notion of energy because you have to apply a field. And in the simplest case, we can always reverse engineer the optimal Hamiltonians to do these unitary gates. In principle, we just have to take the matrix logarithm, or in other words, we find the corresponding time-dependent Hamiltonians that in effect give you exactly the gate operation that you're interested in. And for the Hadamard gate, what you see here is basically just a magnetic field applied in X and Z direction. Now, that we have a notion of energy, we can start thinking about deriving Landauer's principles. I'm not going to walk you through the mathematical details. It's actually a pretty neat derivation. It doesn't take that long. It's just 3-4 lines. Some would even consider it pretty. But let me just talk about the result. What you get is after a few lines is that the change of the Shannon information, which I'm writing here in units of bits, is upper bounded by stuff, natural constants. There's an H bar in there. Okay, fine. It's quantum dynamics. Depends on the dimension of the Hilbert space. The dimension of the Hilbert space replaces the notion of temperature for very good reasons. We're talking about unitary processes. We don't have notions of temperature because we're not in equilibrium. And then something that for some of you might look very exciting and very familiar, and for others of you might look a little bit strange. So what you get is the time average of the norm of the Hamiltonian. So if you work in quantum control or in quantum speed limits or shortcuts, what you immediately recognize is that, yeah, this is the cost function that we've been working with for 10 years. This is what always pops up. For positive semi-definite Hamiltonians, and that's just a remark for the experts, that's basically just the average energy that we're looking at. Norm of the Hamiltonians means sum of energy eigenvalues. A little bit more physically, more practically, what we're looking at here is if the Hamiltonian describes magnetic fields, then what we're really looking at is just the average intensity of the magnetic field with which the qubit operation was done. So that's pretty cool, in the sense that we have something that closely resembles Landauer's principle, again, a statement of the second law of thermodynamics, but now here rephrased and re-derived for unitary gate operation. Right, fine. The late Michael Fisher always said, if you have a new result, the first question that you should ask is, so what? So of course you can do a lot of pretty math, you can derive new inequalities, but what is it good for? It's nice that we have a consistent theory, but can we actually do something interesting with it? Well, on the one hand, if you work in quantum control, then you immediately see, well, this is the cost functional that you want to minimize, and you can find optimal control strategies how to do your qubit operation, which is cool. But what I also want to advocate is that these type of bounds can tell us something interesting, which is maybe a little bit overlooked. And what I want to focus on is quantum error correcting codes, mostly because this is something that we've been talking about for the last 2 days. And here, this is the point where what I said earlier becomes important again. What is computationally efficient is not necessarily thermodynamically efficient. And let me illustrate what I mean by that. In classical error correction, assessing the thermodynamic overhead, the energetic price that I have to pay for error correction, is pretty easy to compute. So if you take, again, the repetition code that we've also seen, I think, yesterday already in one of the talks, then it's pretty easy to assess how much you have to pay in energy in order to do the operation. So let's imagine, for instance, that you want to really reliably erase one bit of classical information and you have a usual repetition code. Then what that means is that if you classical repetition code has an n times repetition, n times redundancy, then you have to erase n physical qubits separately, which means the price in order to erase one logical qubit is then just n times the price that you paid for erasing one physical qubit. So it's just n kBt log 2. This works very similarly for the simplest quantum error correcting codes. So for instance, if you look at Shor's code, in Shor's code, which is up here in the first line, you encode a logical qubit in 9 physical qubits. And since we're assessing the energetic cost in terms of the norm is linear in the number of qubits for this linear code, you see that reliably erasing or resetting a single qubit then 9 times as expensive as resetting a single physical qubit. Now, there are many other error correcting codes that do pretty much the same, and you could argue that there's things like perfect codes with minimal overhead, minimal computational overhead. Like, for instance, there's this thing where the overhead only has 5 physical qubits for a logical qubit, and you would conclude that if you look at this, that this perfect code is not only computationally more efficient, there's less computational overhead, but that it's also thermodynamically more efficient. However, what this is overlooking, and this brings me back to the sketch that I had previously, is that you actually need to encode the information in your logical basis. And you can probably easily convince yourself that preparing these states is thermodynamically a lot more expensive than the previous one. Now we're in a very good situation that we can go through pretty much everything that we've seen. And I looked it up last night. There's this quantum error correcting zoo, and there are now more than 600 different codes in there. I think it's 616 or something like that. Most of these codes are nonlinear. Many of them have energy penalties. For instance, the toric code, the surface code that we heard about, it's a nonlinear code, so doesn't scale as linearly anymore as we've seen before. I'm almost done. And if you do error correction for quantum annealers, you have additional energy penalties. And that means that now what we really should do is we should look through all of these error correcting codes and not only assess them with regards to, is it computationally wise to do, but what do we have to pay in energy? And that brings me to the end of my talk. And I hope I could convince you that thermodynamics is still timely, it's still interesting. It's not old-fashioned and stuffy. We just have to rethink how we want to look at resources. There are many other things that are within quantum thermodynamics, and I hope I was able to intrigue you a little bit. If you want to learn more, that's the webpage. Thank you.